sort of from chapter 7 sort of stuff, I believe. So we're going to talk about chemical reactions, chemical equations, and types of reactions, enough that hopefully, like I said, it will kind of give you some information for the lab and help you do the pre-lab and whatever you may need to do. So chapter 7 involves chemical reactions. And there's really sort of 3 reasons why a chemical reaction takes place. And those 3 reasons are really the formation of a solid, which is sometimes referred to as a precipitate, which is sometimes abbreviated as a PPT. It's basically some type of solid formed as a result of mixing a couple of solutions together. Another reason is actually the formation of water. And the last reason why really a reaction takes place is an electron transfer. So kind of like what we were talking about with ionic bonding, those transfer of electrons from one place to another. So really all types of chemical reactions boil down to basically one of those 3 things occurring. You have basically a solid being formed, water being formed, or some electrons have been transferred. When we talk about a chemical reaction, it's a chemical change, which means what you start with and what you end up with are fundamentally different things. There's some type of real fundamental change to the substances that have occurred. We represent a chemical reaction by a chemical equation. And in a chemical equation, on the left-hand side of the arrow are what are referred to as our reactants, and those are our starting material. On the right-hand side of the arrow are what are referred to as our products, which are what are made as a result of the reaction, so what are formed. Now, we use our chemical formulas here in a chemical equation to represent what is being reacted and what is being produced. There are other symbols that we sometimes will see by the chemical formulas, like an S next to it, an L next to it, a G next to it, or even an AQ next to it. S meaning solid, that substance is in the solid phase. L meaning that is in the liquid phase. G meaning it's in the gas phase, and AQ meaning it's in the aqueous phase, which is basically a solution. It's a water environment. To make something that's aqueous, you usually will take like a solid, for example, and dissolve it in a liquid. So as an example of that, if you took water by itself, that is a pure liquid. There's nothing else in it but just water. If you took some water and added to it some solid sodium chloride salt, the salt would dissolve in the water. And what happens is when it dissolves in the water, you will make sodium chloride solution, and that would be an aqueous solution. So something that's aqueous is a solution. It's a homogeneous mixture. Everything looks the same throughout. Everything dissolves. Everything mixes in it. And that is the difference between something that's a liquid and something that is aqueous. Other things that we sometimes will see in chemical equations and in chemical reactions in general are sometimes there's a number of things that are written on top of the arrow to indicate some things that maybe were added to the reaction, or some things that were added to maybe help the reaction take place. So a very common thing that we kind of will see written on top of the arrow are things that are sometimes referred to as catalysts. And catalysts are not reactants. They're not products. And they do not get used up in the reaction. So really a catalyst is just there simply to basically make the reaction occur faster in most cases. So that is basically what a catalyst does. It speeds up a reaction. So for example, instead of everybody just flying around trying to find each other, Maybe everybody's attracted to the catalyst, so everybody ends up in the same location, and that allows everybody to start reacting a lot faster than they would if they were just kind of floating around. So sometimes catalysts can be something as simple as metals. So they'll write something like platinum up there, and it's a metal that's used to speed up the reaction. Sometimes they may write something like H+, which means that it's an acid being used as a catalyst. Some other things that you might find on top of the arrow, sometimes they'll use the delta symbol, which means heat usually. Sometimes you may see on top of the arrow water written, which means something was dissolved in water. So those are very common things that we see on top of equations to describe what's going on in a chemical reaction. Any questions on that there? Now, one thing that we always want to do when we're dealing with a chemical equation is we always want to make sure that it is balanced. And the idea there is the law of conservation of mass, which means the only thing that's happening in a chemical reaction is we're breaking all the bonds on the reactant side, and then new bonds are being formed on the product side. We never lose any elements along the way, which means if we started with like 4 carbons, we should end up with 4 carbons. They may be in different things, but we'll never ever lose any elements along the way in a chemical reaction. They just get really rearranged. So always when we're dealing with a chemical equation, we definitely always want to make sure that the equation is balanced. So how do we balance it? Well, we basically need to make sure that we have the same number of elements on each side. So if we look at an equation such as, actually, let me do like this. Let's say we had H2 plus I2 goes to HI. Now, in this case, when we go to balance the equation, the only thing that we could change are the numbers that come in front, and these are what are referred to as coefficients. And we could use numbers to make sure that we end up with the same elements on each side, or same numbers of elements on each side. There are 2 really main rules when we balance the equation. All the coefficients, when you are all done, need to be whole numbers. And the second rule is they need to be the simplest set of whole numbers. So what I mean by that is if you balance the equation like 4a plus 2b goes to 8c, and that was balanced, you could go through all those coefficients and divide by 2. So you should do that, and that would give you the properly balanced equation that would look something like this in this example. So it is possible, depending on what numbers you look at, that you may be able to balance everything with sort of larger numbers. But if you can go through all the coefficients and reduce them down to whole numbers by dividing by a common number, then you should do that. One really good approach to balancing equations is to make a table. There's like the reactant side and product side, and just list the elements like HI is pretty much all we got going on here. On the left-hand side, we have 2 hydrogens. On the right-hand side, we have just 1. On the left-hand side, we have 2 iodides. On the right-hand side, we have just 1. So a table oftentimes will give you an idea as to where you should start. So in this case, it makes sense to start with the hydrogen. So we'll put a 2 there. And by doing the 2 there, that gives me 2 hydrogens. This number goes to everybody behind it. So it gets distributed to each element. And that would also mean that I have 2 iodides in this case. And that actually would be the balanced equation at this point. So the only thing that we should ever change when we're balancing an equation is the big numbers that come in front. We never should change any of the small numbers because that changes what it is. We should never put big numbers in between letters or anything like that, but always just the numbers in front. Any questions on that there? So why don't you try one here? Let's say we had N2 plus H2 gives me NH3. So why don't you balance that guy up, see what you come up with here. Take a look. So once again, I would recommend maybe making a table. We'll list all of our elements, which in this case is just nitrogen, hydrogen. On the left-hand side, we have 2 nitrogens. Right-hand side, we have just 1. Left-hand side, we have 2 hydrogens. Right-hand side, we have 3. So once again, probably the easiest thing to start with would be the nitrogen in this case. So we could simply balance it by putting a 2 in front of it. Once again, that 2 goes to everybody behind it. So that would be 2 nitrogens. 2 times 3 is 6 hydrogens. So what usually happens in this case is you fix one thing, kind of mess something else up, but that's okay because we could then go to the other side and we could fix the hydrogens by putting a 3 in front of it. And if we put a 3 in front of it, gives me 2 nitrogens. And once again, 3 times 2 is 6 hydrogens. So that would be balanced in that case. Any questions on that one there? Now, if you had, say, C3H8 plus O2, CO2 plus water, give that one a go, see what you come up with. Okay, let's take a look. So once again, here we'll make like a little table to help us out. And we have reactants, we have products, we have carbon, hydrogen, and oxygen. Left-hand side, we have 3 carbons. Right-hand side, we have just 1. Left-hand side, we have 8 hydrogens. Right-hand side, we have 2. Left-hand side, we have 2 oxygens. Right-hand side, how many oxygens we have? You have 3, 2 there, and 1 there is 3. So in this particular case here, carbon seems pretty easy. We could put a 3 here. That would then go to each of those guys there. That would give us 3 carbons. It would also still give us 2 hydrogens. Now, in terms of oxygen, we have 6 here and 1 here. It's a grand total of 7 at this point. At this point, we could then fix the hydrogen, probably the easiest because we have oxygen in a lot of places over there. So to fix the hydrogen, we could put a 4 in front of that. And again, that's going to go to everybody behind it. And that would give us still 3 carbons. Hydrogen would be 4 times 2, which is 8. Oxygens, we have 6 in the first one. And now with the 4, we would have a grand total of 10 at this point. Yeah. Any questions on that there? So again, 6 in the first one from here. And 4 more there gives us 10. At this point, we could fix the oxygen by going to the left and putting a 5. And that would give us 3, 8, and 10. Any questions on that there? Okay, let's try just a couple more here. Let's try one that looks similar. Let's try C2H6 plus O2, CO2 plus water. And let's try this one here, Fe. Let's do FeSO4 plus a little silver nitrate. There we go. All right. Balance those guys up, see what you come up with. Okay, let's take a look and talk about some things that could come up as you're balancing equation, like maybe you're running into in a couple of these problems here. We'll start like normal. So we'll make our chart here, reactants and products. We have, again, carbon, hydrogen, and oxygen. On the left-hand side, we got 2 carbons. Right-hand side, we have 1. Left-hand side, we have 6 hydrogens. Right-hand side, we have 2 oxygens on the left. And once again, we are starting with 3 oxygens on the right. So you probably approach the same way. Start with carbon, and we could put a 2 in front. And when we do that, that gives us 2 carbons, still gives us 2 hydrogens. Once again, that's going to go for both of them. So there's 4 oxygens there, plus 1 more there gives us 5 oxygens at this point. Now, probably again, the easiest thing to fix at this point would be the hydrogen, because again, oxygen's in a lot of places at this point. So we could fix the hydrogen on the right by putting a 3 in front of the water. That gives us 2 for the carbon. 3 times 2 is 6 for the hydrogen. And now in terms of our oxygen, we again got 4 here. And 3 times 1 is 3, which gives us 7 at this point, right? Now, at this point, we clearly don't want to play with the numbers we did on the right-hand side. Yeah. Yeah. When I put the, before I put the 3 up there, there was 4 here and only 1 here, which is why there's 5. Yeah. 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 Could you have started with the oxygen instead of the or could you start with the you would, because the 5 came from putting a 2 in front of this carbon. Yeah. Yeah. Yep. Other questions? Okay, so at this point, we clearly don't want to touch anything on the right-hand side because we're undoing our work here. So really what we're left with is, this is the only place where there is oxygen, right? And there's 2. So we really need to turn a 2 into a 7. And we could do that with a fraction will allow you to actually turn a 2 into a 7. If you took something like 7 divided by 2. Now, if we look at what we got, I have 2 carbons on the left. I have 6 hydrogens. And when you take 7 over 2 times 2, the 2's cancel and you end up with 7 for the oxygen. It is technically balanced at this point, but the one thing that you should always have at the end is all whole numbers. So this would not be the properly balanced equation because the coefficient there is 7 over 2 is not a whole number. So this illustrates that sometimes you do need to use a fraction to balance the equation, but you cannot leave the fraction there. So you got to get rid of the fraction. To get rid of the fraction, you need to multiply the entire equation by the denominator, right? So we're going to times everything by 2 here. And when you do that, you will end up with 2 of the C2H6 plus 7 oxygens gives us 4 CO2 plus 6 waters. And if we didn't screw up here, this would actually now still be balanced. We have on the left-hand side 4 carbons. Left-hand side, we have 12 hydrogens, multiplying this 2. And we have 14 oxygens on the left-hand side, multiplying the 7 to the 2. On the right-hand side, we have 4 carbons. We have 6 times 2, which is 12 hydrogens. And we have 8 oxygens there and 6 oxygens there, which is 14. So very commonly, or sometimes in the cases like this where you have one element by itself, like O2, N2, something like that, and you have that same element and multiple things on the right-hand side, sometimes you do need to kind of use a fraction to balance the equation, but you do have to get rid of the fraction when you're all said and done. Now, you may be wondering, how do you pick the fraction? It's a very simple recipe. The top number is the number you need. So if you remember, we needed 7 over there, so that's why we chose 7. The bottom number should match the subscript, which is this number. These two should match. So that's always how you could choose sort of the right fraction. Top number, the one you need. Bottom number should match the guy on the bottom, and then everything will cancel out correctly. So you could use a fraction, but you do got to get rid of it by clearing the fraction and multiplying everybody by 2 to end up with all whole numbers here when we're all said and done. Any questions on that there? Okay, so this last one here, we could hopefully recognize some things like some polyatomic ions. And whenever you have some polyatomic ions that look the same on both sides, it is a lot of times easier not to break it apart into individual elements, but just to balance the polyatomic ions as units. So what I mean by that is we could start with either one. In this case, we have one SO4 unit here and one of them over here. So we really don't have to do anything with that. On the left-hand side, we have how many NO3s? 2. On the right-hand side, we have just 1. So that's what we would want to fix by putting a 2 in front of it. That now gives us 2 of the NO3s. And it now gives us, though, how many silvers? 2, which is good because that's like what we need. So we're actually done at this point. So it's a much quicker and much faster a lot of times when you have polyatomic ions to keep them together than going individually element by element, so you don't have a lot of multiplying in and multiplying out. And what will usually happen is what we just did there, everything will sort of fall into place by doing that. So you put the number in front to take care of the polyatomic ion, then you take care of the guy in front, and that's where you should go next to balance it. Question on balancing. Okay. The other thing I want to talk about in terms of reactions to help you out is types of reactions and ways to classify reactions. There's a few different types of reactions. First type of reaction is what is known as a synthesis, or sometimes referred to as a combination reaction. And basically, it is kind of like what it sounds like. You take 2 things and you make 1 thing. So that is the general form of a combination or synthesis. So if you took some H2 plus some O2, that makes some H2O. We'll balance it here. That is 2 things that make 1 thing. That is a synthesis or combination reaction. Take some magnesium plus some oxygen, make some magnesium oxide. That is 2 things that make 1 thing. Classic setup for a synthesis or combination reaction. The sort of opposite of that is a decomposition reaction. And in a decomposition reaction, you'd start with 1 thing and you make a couple of things or more. So you basically break it apart. So synthesis and combination, you put it together. Decomposition, you take 1 thing and you break it apart into a bunch. If you run an electrical current over water, you can actually break it apart into hydrogen gas and oxygen gas. 1 thing makes multiple things is a decomposition reaction. If you took some KClO3 and you heat it up, it will make KCl plus a little oxygen there, put a 2 there, maybe a 2 there, and maybe a 3 there. But 1 thing makes multiple things, basically a decomposition. So that's what you want to look at when you're looking at an equation. You know, 2 things make 1, synthesis or combination. 1 thing makes multiple things on the other side of the arrow, decomposition type reaction. Any questions on that there? Couple other classifications is a single replacement reaction. And sometimes people call a single displacement or single exchange, but a single replacement is when you have 1 thing by itself plus an ionic thing. So this is like an ionic thing. And if this is a metal by itself, it has no charge, it will come in and kick out the positive guy. And when it kicks out the positive guy, a new ionic compound will form where that guy will get a charge. And the guy that was there originally would come out by itself. You could also do this with a non-metal, and it would kick out the negative guy. It works the same way, but if you took something, say, like zinc, and you add it to some hydrochloric acid. So this has no charge, but this has a positive negative charge. And when zinc does make a charge, it makes a positive charge, and it would come in and kick out the hydrogen. When it kicks out the hydrogen, hydrogen comes out by itself. And when hydrogen is by itself, not attached to anything else, it is hydrogen gas. You would see bubbles starting to form in the test tube. And then zinc would actually get a charge at that point, which is +2, and make some zinc chloride in this case. and balance it here, put a 2 there as well. And that is a single replacement reaction. In order for that reaction to take place, whatever is coming in needs to be more reactive than what is replacing. If it's less reactive, the reaction will not happen. So for example, if you swapped out zinc for copper and you did the same reaction, you would get no reaction take place because copper is less reactive than hydrogen. So it will not be able to kick it out in that reaction. As I said before, you could also do it with a nonmetal, works the same way, except that the nonmetal would kick out the negative charge guy and give us our C by itself and a new ionic compound that looks something like this. So it can work for both. Any questions on a single replacement? So one guy comes in, kicks out the other guy, and that is single replacement. The other type of reaction is a double displacement reaction, I think is what you have in your lab, if I'm not mistaken. So let's take a look at what that is. That is a double displacement reaction. And that is AB plus CD. You could recognize these as two ionic compounds, so two things with charges. And what happens is the two things that are positively charged will switch partners and we'll make an A and a D plus a C and a B. And what will happen in this case is sometimes one of these guys will make a solid, which is referred to as a precipitation reaction. Or one of these guys may make water, which is again one of the two reasons why a reaction takes place. So if you took some silver nitrate, which you probably will do, be careful, it stains your skin, plus some sodium chloride, we could recognize this as a double displacement reaction because again, that's a positive negative guy, positive negative. These two guys will switch partners. The sodium will come together with the nitrate and the silver will come together with the chloride and that will make a solid. And that is a classic sort of double displacement reaction. Basically, the two positive guys switch partners on the other side. And again, this would be considered a precipitation reaction because you made a solid in this particular case. So double displacement, you could recognize because you're starting with two ionic compounds. Single replacement, you're starting with only one ionic compound. So that's the difference between those two. Lastly is a combustion reaction. And most people, when they look at a combustion reaction, is some type of organic guy, like carbon, hydrogen, or oxygen, plus O2 and CO2 and water is always what you get. It's like what happens when you light your Bunsen burner. It's all those reactions we just balanced with, looks just like that. So if you see O2 and CO2 and water, it's probably a combustion reaction. There is a generic combustion reaction, which technically means all you need for it to be a combustion reaction is that on the left-hand side. So if you had something like what I wrote earlier, technically, even though that's a synthesis reaction, it could also be classified as a combustion reaction because it technically has O2 in it. So the basic general definition of combustion is you got to have O2 on the left-hand side of the arrow. But most people, when they talk about combustion reactions, the organic combustion, where you have O2 on the left, CO2 and water, is always the products that are formed in a combustion reaction that involves an organic compound. There are multiple ways you can classify the same reaction depending on what you're looking at, but these are sort of the big categories that I think is in your lab there. Any questions on that? Okay, so we'll lay that up there. Hopefully that'll be helpful for your lab this week.